Greetings and welcome, friends. Today we're going to learn our final technique for solving non-right triangles. Because you might be wondering, up to this point, right, Pythagorean theorem and our trig ratios, those work great for right triangles. And Law of Cosines works good for a lot of triangles as well. However, there are two situations that we have yet to been able to solve. One of them are side angle side situations, in which I give you two sides and their included angle. And then the other one is a side-side-side situation, which I guess arguably maybe you could solve these with Law of Sines using like writing multiple equations and multiple unknowns. And through some degree of doing all that, you could figure that all out. But we're going to do Law of Cosines today, which conveniently is going to allow us to solve both of those cases. So, first things first though, we've got to earn the right to use the Law of Cosines. So that means we're going to prove it for us right now. We're going to derive it. I guess, yeah, I'll write derive. All right, we're going to derive this. This is going to be good. So let me draw a picture of a triangle here. So here we go. I'm going to try to draw this big because it's going to have other components to it. Let's see. Here we are. And yeah, that's good. That's good. Not bad. So I'll label this. So try to, draw this picture. Here we are, A, B, and C. And so if that's A, B, and C, then this must be little c, this must be little b. This entire length is going to be little a. And I'm very intentional in labeling this entire length because I'm going to break it up in a moment. So suppose I was to draw the height down from A. Okay, so here's my height. It meets at a right angle, of course, by default. And my question for you is, let's see, if I decided to label this dimension x, all right, right here. So x goes from here to here. Could you figure out a label for this dimension? And don't just give it a variable name like y or something like that. But in terms of the variables that I already have listed here, the components I already have, what would this length be? Well, okay, you're taking it back to the Law of Sines ambiguous case. But yeah, if I'm relating it to these two, notice I would have this length plus this length is equal to the whole length, right? Right, whole length is equal to the sum of these little parts. So similarly, the whole length minus this length would give me the scrap left over. All right, so this distance is actually going to be a minus x. All right, I want to try to, if I said a prime, it would actually be introducing another variable. It looks similar, but it would still count as a different variable. So I want to try to keep the number of variables I have at a minimum, so then I'll be able to hopefully solve and derive this formula for us. So, all right, let's take a look at some of these. And I'm going to actually pull three separate equations out of this and then combine them into a simplified one that will relate either it'll actually relate one of my angles and 2 or 3 of my sides is what it will end up doing. So hopefully I'll be able to get rid of these x's because you guys don't know what the length x is in any of our triangles, and that's fine. We don't need to know that just yet. So let's see, the first thing I want us to consider is this right triangle here. All right. Actually, I guess I could label the height there as well. I'll label that h. This right triangle here, what equation would I get if I used Pythagorean theorem on that? What would that equation look like? A minus x all squared plus perfect, plus h squared equals c squared, right? So there's the first fact that I've got from this little setup here. And a minus x all squared, I could actually expand that out, and I'm going to do that. We can actually do that using a pattern. You might remember from your previous math classes, that's going to be a squared minus 2ax plus x squared is what that expands out to be. And then it'll still have the plus h squared hanging out equals c squared. All right? So there's my first thing, and I've reached somewhat of a dead end right now. Let's see, another fact I could gather. Let's do Pythagorean theorem with this side. What's that going to tell me? Or I'm going to switch it around just a little bit for sake of friendliness, but you are not wrong. X squared plus h squared equals b squared. And the reason I'm doing this is very particularly, have I seen another x squared plus h squared anywhere in my work so far?
Yeah, kind of.
Yeah, right down here, right? So if b squared is really equal to x squared plus h squared, that means I should be able to replace this through substitution, right? So that's one thing I'll end up doing. So I can actually replace that with just b squared. And notice that will actually get rid of one of my x squared terms. So that's good news, right? Really good news. I'll hold off on just a second because I'm going to write one more relationship that will be helpful for us because I still have this x that I want to get rid of. So I want to write another equation in terms of x. And so it's probably going to be from this triangle that I'll be able to write another relationship or equation from. I wouldn't necessarily want to relate it to h because I just got rid of an h as well, and h isn't necessarily a given piece of information. If I'm given something like side angle side or side side side, they didn't give us the h. We just know the sides and angles or something like that, right? So I'd probably want to relate x and b. So from this triangle's perspective, let's see. I know this is a 90-degree angle. This angle up here is technically not equal to one of the ones given to me, right? Because this whole angle is A. This would be some portion less than A, not necessarily half of it. In fact, it's unlikely it will be half of it. So the angle that I do know that's given with a triangle is this. So could you guys write an equation that relates these facts, these three pieces of information, for a right triangle? Challenge.
Sine of c over h equals...
Well, I don't want to use h, but I agree it's going to be a trig ratio from this angle's perspective. What is this side from angle C's perspective? Adjacent, and this is the hypotenuse because it's opposite the right angle. So what trig ratio would compare those three things for me? Cosine. Cosine. So I could say that cosine of angle C is equal to adjacent to hypotenuse, so that's x over b, right? And what did I say I was trying to get rid of? I want to get rid of this other x. So it'd be nice if I could actually solve this equation for x and then substitute again, right? So how could I solve this equation for x? Multiply both sides by b. And I'll end up getting x equals b times the cosine of c. And now if x is truly, truly equal to that, then that means I could replace x with that at any point. All right, so I'm going to double substitute here. Right, so I had actually three starting points. I had this equation, I had this equation, and I had this equation. And I'm kind of like pulling them all together to eliminate variables. All right, and just try to simplify this into a fact that's very easy to see. So let's see. So what's this going to look like as my final product? It's going to be a squared minus 2 times a times, and instead of x, it's going to be b cosine of c. And then x squared plus h squared is being replaced with a b squared. And that's equal to c squared. Now let me rewrite this a little bit, just a tad. So this is going to be one of our versions of the law of cosines. And you can probably gather that it gets its name from the fact that it's got a cosine in it. And the law of sines had a sine in it. Right? Pretty good names for these. And I'm going to rearrange this just a little bit. And in fact, I'm going to write this as my third line down here because I'm going to have three variations of it. So the third one is going to be c squared is equal to, all right, so I'm writing it backwards a bit, a squared plus b squared. All right, because notice here's the a squared plus b squared. And then the only piece that I'm missing so far is the minus 2ab cosine c. So minus 2ab times the cosine of c. All right, and this is going to be one of my law of cosine variations. Okay? And now I want you to actually think about it like this. So what is this part of it? That's the Pythagorean theorem. So think about it kind of like this. The law of cosines is essentially a Pythagorean theorem where I subtract some extra. All right? Well, I'm subtracting specifically when the angle C is acute, because then cosine's in the first quadrant. Cosine's positive in the first quadrant. So I'm subtracting some leftovers to make this true. And if cosine's in the second quadrant, cosine's negatives, and a negative times a negative would be positive. So in the case of a second quadrant angle, if I have an obtuse triangle, I'll actually be adding some extra to make this equation true. So this is kind of like Pythagorean theorem-ish with like this little extra modification to it. It's kind of like how we have a calendar for the year that has 365 days, and then every 4 years I end up having to modify the calendar a little bit with a leap day because it's technically 365 and a quarter-ish days in a year. So we just have like this little modification to tweak it so that we're right? We're calibrating it, so to speak. All right, so this is the law of cosine, and notice the things that the law of cosine relates. It relates three sides, right? AB, AB, so those are the two sides. There's C, so AB and C, and one angle. So there's four pieces of information. And typically when I'm using an equation or a formula, if I have, if I can plug in all of the information except for one, I know I'll be able to solve for the last piece of information. So this law of cosines will work anytime I have 3 out of the 4 pieces of information. I could then solve for the fourth piece. So if I know 2 sides and an angle, right? So if I know AB and angle C, I could easily find side C, right? But it turns out it'll also work if I know all 3 sides, and then I'll have this unknown angle, right? And in that case, I would end up having to plug all those in, get cosine by itself, and then how would I get this final C by itself, do you suspect? Inverse. Yeah, I'd cosine inverse both sides once I'm all said and done. All right, so this is going to allow us to work with either 3 sides and find an angle, or 2 sides and an angle, which is what I was describing up here a moment ago. This is going to work for our side angle side and our side 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 situation. Now, as I said a moment ago, this is one version of the law of cosines. I could, if I had renamed where my A, B, and C were, or resolved this multiple times, or if I drew the height here this time, or if I drew the height here this time, that was a terrible height, I would actually end up solving this a few different ways. Actually, I'm going to leave that out. So the other way would be solve for A squared and B squared. All right. And the A squared one, now let's see if you can figure out this little patternish thing going on. So A squared is going to equal B squared plus C squared minus 2 times BC times the cosine of what angle do you think this is going to be? A, angle A, exactly. Right, so you can see that here when I had little side C by itself, I had angle big C being my angle. So if I have little angle A by itself, I've got angle big A as the angle that's given to me, or the angle that I'm looking for. So then let's see, for the B squared version, that's going to equal A squared plus C squared minus 2 times AC times the cosine of B. So there's the 3 versions of it. I don't think it's terribly difficult to memorize those because I see that this is, you know, when it's AB, then this is AB. When it's AC, then this is AC. When it's BC, then this is BC. And then, like I said, the angle just matches the one that's by itself. So that's how I kind of memorize it. It's not terribly difficult to memorize. And they're all just little modifications or variations of one another. So now that we've proven it, 15 minutes into the video, let's get to our 2 examples. And just 2 that I'm doing today. Example. Solve the triangle. Okay? And hopefully it's a situation that uses law of cosines, because that would be helpful to us. So suppose my triangle looks like this. It's going to be an obtuse triangle. Yeah, good enough. All right, and I'm going to have the following information. I'll have a 124 degree angle, and I'll have one of its adjacent sides be 10, and the other adjacent side be 7. Now, one thing I'm going to let you know in advance is that there is no ambiguous case of the law of cosines. There's only ever one triangle possible for law of cosines, okay? Because side angle side was always conclusive as well as side side side. There's only one triangle that can be formed from that information. So I might as well, I guess, also label this. Now, you won't always necessarily have labels given to you. I don't know, let's label this A, I guess, and then, I don't know, B and C. I don't know, it doesn't matter to me. That'll do. So if I want to use a law of cosines that relates this according to my current labels, which angle do I know? A. So I'm going to use the law of cosines formula that relates to angle A. All right. And what piece of information is this going to help me solve? Well, angle A and side A is the next piece of information I'm looking for, and that's exactly what I'm going to get there. So let's plug this into that formula and solve it. So I'll have a squared equals, let's see, b squared is 7, right, 7 squared, plus c squared is 10, so 10 squared, minus 2 times 7 times 10 times cosine of 124 degrees. All right, so I just plug it in. I want to point out that this is a multiplication sign here. A lot of times students end up messing up their PEMDAS is what they end up doing. So let's see, a squared equals, let's see, 49 plus 100 minus 2 times 7 is 14 times 10 is 140 times the cosine of 124. Actually, I'll evaluate what cosine of 124 is, estimate it. I know it's going to be negative because cosine's negative in a second quadrant and a 124 degree angle is in the second quadrant. So this is going to be multiplied by negative 0.55992, we'll call it. So let's see, to get a squared by itself, let's see, a squared equals, now this is where people get excited, 149 minus, and they'll see 149 minus 40, and they'll be like, or 140, and they'll immediately be like, that's 9! But we have to be careful, multiplication has to take place prior to that. All right, so just be aware of that. I'm actually going to multiply the 140 by my cosine here. And actually the cosine was negative. Negative times a negative, this is going to become a plus, right?
Okay, thank you.
78.29 roughly. So a squared is equal to that with 149. So I get 227.29. And now how would I get a by itself, do you suspect? Root both sides. Now technically, algebraically, I should write a plus or minus here. Geometrically, though, I'm not expecting a negative value for a because I want this to be a distance and distances are positive. All right, so you can discard the minus version right away. All right, it's just going to be the positive. So I'll get a is approximately, let's see, square root of second answer, 15.08. Right, so I've just been able to find this missing side. Using law of cosines, law of sines would not have been helpful unless I did multiple laws of sines and made a system of equations and maybe solved it using Kramer's rule or matrices or something. And now that I found side A, notice I actually have a pair of an angle and a side. So now law of sines can show up and just mop up the mess, right? Where I can just be like, all right, I could actually find angle B or angle C. It doesn't matter which. I don't know, let's find angle B for fun. So that is now a law of sine situation where I'm comparing the angle to its side, angle, side, we know what's up. So angle B, so I'm going to have sine of B over 7 is going to equal the sine of the angle I had, 124 degrees. Is sine of 124 positive or negative? Positive. Because sine is positive in the second quadrant, remember? Yeah, well, I'm using law of sines now. So law of cosines just gave me the step. Usually you'll only end up using law of cosines once. You won't necessarily have to use it back to back. I mean, technically well, could we? Yeah, technically now that I have this side and this side and this side, I could actually have plugged all three of those into this for all the sides and then found B that way. I mean, I could have, but we're so good at law of sines at this point, and it's actually less work to do law of sines. So I just want to point that out. Use law of sines once you're that far. So sine of B equals 7 over 15.08 multiplied by the sine of 124 degrees. And how do I get the angle by itself? Sine inverse. Everybody loves it. And sine inverse, we know that if I give sine inverse a ratio, it gives me what back? An angle. So let's see, this is going to be second sine inverse of 7 divided by, second answer, I happen to have 15.08 in my calculator with all of its other decimals, times the sine of 124, double close parentheses, and I get 22.64 degrees. And now technically, to find my third angle, I could use law of sines. I could use law of cosines, but why waste our time? I could just use triangle sum. Right? So angle C, much easier to find using this technique. 180 minus parentheses, second answer, plus 124 close parentheses, and I get angle C equals 33.36 degrees. Right? So congratulations, we have just solved one of our last unsolvable triangles. Not bad at all. And you can always relate this. So let's see, what did I just say? I said this was like 33. I said, what was angle B? 22. Right. So you can see that the biggest side is opposite the biggest angle. The smallest side and angle are opposites, and the mediumest are opposites. Right. So you can kind of always do that last check at the end, like, is this a reasonable answer? So that way you're confident in your results. So let's do one last example, because we haven't done a side-side-side situation yet. And I want to make, like, you guys got to believe me, right? Like, I mean, I want to prove it to you beyond a shadow of a doubt. So let's solve the triangle. And let's say this triangle is a something like this, and I'll label its dimensions as such. This will be a 3, 4, 6 triangle, not a 3, 4, 5. If it was 3, 4, 5, I know it would have had a right angle. Let's see. Actually, you might be able to determine this right off the bat. If 3, 4, 5 is a right angle, 3, 4, 6, what kind of angle do you think this will be? Well, 3, 4, 5 would have looked like this. And imagine this side stretching it further, this angle would get bigger, so it would actually be an obtuse angle. All right, so just pointing that out. So let's see, this came unlabeled to us. I don't know, let's make 6 the hypothetical hypotenuse, even though I just determined that it is not. And then we'll make B the one up, the medium one, and A the small one. I don't know, it doesn't matter. So I've got 3 sides. I want to find an angle. Law of cosines will help me out. I can relate 3 sides and then find the missing angle. All right, and it doesn't matter which angle I find first. All right, whichever one of these versions of law of cosines will help me out in this case. So which angle do you guys want to find first? You got a preference? Let's find A, sure. Let's find little A. The little cute one there. So if I'm looking for angle A, then side A is going to be what I'm plugging into my law of cosines. So 3 squared is going to be the one that's on the left-hand side there, equals 4 squared plus 6 squared minus 2 times 4 times 6 times, and actually this is a mistake that students make, they'll plug in sine instead of cosine for the law of cosines. So make sure you're using the right trig function. Because we're so used to law of sines, we're just like, we're sining everything, right? But no, that's not what we'd want to do. And this is cosine of angle A. So let's simplify this. That's 9 equals 16 plus 36 minus 2 times 4 is 8 times 6. 48. Whew. I always get scared on that one. Times cosine A. So 9 equals 16 plus 36. Let's see, that's going to be 52, is it? And this is where students are like, oh, 52 minus 48, I can do that. It's like, hold your horses, right? We've got to PEMDAS this. Multiplication comes before subtraction. So I can't do that, all right? So I'm going to now start solving this for the A. This 52 is the first thing I'll move. I'll subtract 52 from both sides. Let's see. Yeah, it's a super common mistake, and that's why I like pointing it out. Hopefully avoid the pitfall there. Well, it's so tempting, too. And like usually they're really close in value, and it's just like, oh, it's so tempting. They're just like, yeah, that'll work out great. So let's see. Now, how would I get rid of this negative 48? Exactly. That's another thing students sometimes do. They're like, oh, let's add 48. But remember, the negative 48 is being multiplied by this thing. So to get rid of it, I have to undo the multiplication, which is divide. All right, I like this. Divide by negative 48. And I'm going to get cosine of A. I almost said alpha. Those minus signs will cancel out. I guess I could leave that as 43/48 for now. And just plug it in when I do my next step. Which, how would I get A by itself? Cosine inverse. Man, you guys are so good at this. I love it. Cosine inverse. So angle A is approximately going to be the cosine inverse of that ratio, and I get 26.38 degrees. $26.38. All right, so for my little sketch, I don't need to have all the decimals. So now to find another angle, I could use law of cosines. All right, I could do this whole setup again and all this work, but I think law of sines is quicker, and I want to use law of sines because notice I've got an angle in its side. And so now I could say find angle B just using straight up law of sines, which I can cruise through this because we're so good at it. Sine B over 4 is going to equal, let's see, what was side A again? 3. Nope. Sine of the angle first, 26.38 degrees over 3. And then to solve for B, of course, we multiply by 4. And you guys could, you know the law of sines with your eyes closed these days. So we'll get sine of B equals 4/3 times the sine of 26.38 degrees. And to get B by itself, inverse both sides. So I'll get angle B is equal to sine inverse, second sine, of 4 divided by 3 multiplied by the sine. So I'm using sines now, not cosines, just pointing out, of second answer, double close parentheses, and I get 36.34 degrees. And as I pointed out in the last problem, we could use law of cosines to find the next angle. We could use law of sines to find the next angle, but better yet, I know 2 out of 3 angles. So let's just use triangle sum. Right, so we'll just do angle C is equal to 180 minus A plus B. And so angle C minus, I've got the 36 already in there, so second answer, plus 26.38, close parentheses. And I get angle C, this happened to be an obtuse one again, 117.28 degrees. So, the benefits of law of cosine, when you want to use it, all right, or actually when you'd have to use it, are when you have a side, side, side situation, right? I was given 3 sides. Or when you have a side angle side situation. All right, that's when you want to use it. And in fact, I believe I also have on our little chart, I have, all right, solving triangles chart. All right, it's non-right triangle. If it's angle, angle side, use law of sines. If it's angle, side, side, use law of sines after considering how many possibilities there are using our other follow-up chart. If it's side, angle, side, you use law of cosines to find your first side, and then you use law of sines to find your next angle, go from there. And if it's side, 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 well, you don't have to find another side. We're good. And the angle you would find using law of cosines and then law of sines from there. So it kind of breaks it down on how to do this based on all of those situations. And that's pretty much every kind of triangle. We just did it. At least triangles on 2 dimensions, right? So don't go crazy now. So thanks for watching, Internet friends. Have a great day. Bye-bye.